Hello everyone. In this video, we will discuss about viscosity. So at first, let us discuss why do we require the understanding of viscosity in fluid mechanics. Basically, by using viscosity, you can measure the fluidity of any fluid, which you cannot simply measure or have an assumption using density or specific weight of that particular fluid. So as you can see, I have already written the formula which you can use in viscosity in this chapter. So this is tau. Tau equal to this is what you call dynamic viscosity. This is pronounced as mu. Du dy. This is the velocity gradient. This is the velocity gradient. Okay. Sometimes you may see is this du dy velocity gradient is equal to d theta dt. Okay, so what is this d theta dt? This is basically the shear strain rate or rate of angular deformation. So we will discuss all of them, and we will also derive this formula, the formula that you can see over here. We will also derive this formula entirely. So at first, let us have a basic discussion of viscosity. Okay, so viscosity, as you can see, I have categorized it into two types. One is mu and other is nu. So basically, what does it mean? Mu, it is the dynamic viscosity. It can also be termed as viscosity. Viscosity itself is this. Okay, viscosity itself is the dynamic viscosity or absolute viscosity, and it has another category or type which you can term as kinematic viscosity. This is new. Okay, so we will see the correlation between them, and we'll also move forward with the understanding of this phenomenon. See, at this point, the velocity, if you consider it as will be zero. The velocity is zero. So as you move forward, you will see that there is another adjacent fluid particle, and above that there will be another adjacent fluid particle. Above that there will be another adjacent fluid particle. So basically there is a layer of fluid particles. Basically there you will find a layer of different fluid particles, one after another, one above the another. Okay, so you can define viscosity as the internal resistance between two adjacent fluid particle when it is in motion. So see, you may have heard about two forces. One is adhesive force, and the other is cohesion. So adhesive force, see here, the adhesive force will be between the this pipe. Adhesive force will be between this pipe and the fluid particle. This is going to be an adhesive force, and above that, and if you consider this fluid particle and this fluid particle, there will be cohesion force between them. And if you consider this plate and this particle, the closer particle to this plate will be having the adhesive force. In case if it is very strong, then this particle will have no motion. This particle will be at zero motion. If you consider this, and in that case, you will see slight internal resistances among the adjacent fluids. So that will create the viscosity, and you can somehow define viscosity in that way. So this is basically nothing but the resistance to flow or deformation. So see, I have already discussed you that what is a fluid, right? So in a fluid, no matter how the small, suppose this is your fluid. So no matter how the small your tangential or the shear force is, there will be a deformation. But in case of a solid, no matter how the small force, this statement is not applicable here, because if you want to deform any solid object, this is your solid object. If you want to deform a solid object, there will be some issues like this. This will be deformed in this way, in this way. This will be deformed in this way, and there will be an angle here. This angle, this will be the strain. Okay, in this case, shear strain. So you can figure it out. We have already discussed, and we have already known about all of the things in our SOM, solid mechanics. So in order to deform a solid, you need to provide a minimum tangential force, which will create this solid object to deform in this way, But in case of a fluid, no matter how the minimum your amount of force is, this fluid will start deforming in such a way like this. Particle by particle, it will get deformed. So this is how you can illustrate, you can imagine viscosity. Now that we have already discussed about the basic definition and need for viscosity, we are going to derive the equation that you had seen earlier, tau equal to nu du dy, or you can also say nu d theta dt. Okay, du dy is the velocity gradient, d theta dt is the angular deformation rate, or you can also term it as shear strain or strain rate. Okay, so and here this is your viscosity, or it can also be termed as absolute viscosity, dynamic viscosity. Okay, so now take a very close look at this picture. Okay, at this picture, as you move forward, you can see this velocity profile. So this is your velocity profile. This is your velocity profile. So in this velocity profile, you can see, if you analyze the velocity of this particle is having u velocity. Okay, u meter per second. The motion of this particle is u, and and above that you have got another particle which is having u plus du amount of motion, u plus du. So you can consider a little bit of changed amount of motion, and you add that distance between them is dy, and this distance and this distance will be having du amount of magnitude, because you have already assumed that the changed velocity is having du. Okay, so now as we move forward, I have just zoomed this entire picture, where I'm showing you that this portion is having u amount of velocity, and this portion is having u plus du amount of velocity. See, I have just taken this, and the distance between them is dy, as you can see here. So it is dy, and the fluid flow is from here. So now I am assuming that from this point to this point, this is the initial point now, and as the fluid is flowing, it is definitely exerting some tangential force, which further is leading to this deformation. And as it is a very close look, as it is a zoomed in view, so I am assuming that there is a straight line between them, as it is a curved line. But as we have zoomed it in, so I can say that I'm having a straight line. Okay, so and after that you assume that the angle that by which it has deflected is d theta. Okay, so now what is the distance, what is the displacement from this point to this point? What is that going to be? So let me tell you that you all may have heard about this formula, S is equals to Vt, right? So S equals to Vt, it means displacement is equal to your velocity times the time. So now I am going to show you that. So from this point to this point, as the velocity is u, so and the changed in time, as it is a fluctuations of second, it's a very short time. So I assume that this is dt. Okay, so from this point to this point you have udt, and from this point to this point, you have u plus du into dt, because your velocity is this amount, and this amount is your time. So you can relate it very easily, right? Okay, so now as this amount and this much amount is same, you can see from the geometric or schematic figure, and this amount will remain as du dt. Okay, so if you break it down, you will find udt plus du dt. So udt is here, and du dt will be here. Okay, so now I'm going to simply calculate all of the things. So see, from this point, if I assume that this is A, this is B, and this is C. So in the triangle ABC, in the triangle A, B, and C, what you see is tan d theta. Okay, so you see that this is the right angle. So tan d theta is simply going to give you du dt over dy. So now, as this angle is very small, d theta is very small. So d theta will be almost equal to tan d theta. Okay, so I can write d theta in place of tan d theta, which will give me du dt over dy. So what you will get from here, d theta dt, which will be equal to du dy. So as I told you earlier, that you can further write this formula as this. Okay, in place of du dy, you definitely can write d theta dt. Okay, so now I have already proved that as well. I have proved through my statement here. So you can very easily understand this. So now what I am going to do is I am going to teach you the Newton's law of viscosity. So what does it even mean? So Newton's law of viscosity. So this will simply tell you that the shear stress is proportional to the velocity gradient, which is simply du dy, and it can also be proportional to, or you can say that the tau, which is the shear stress, is proportional to d theta dt, which is what? D theta dt, what? You can write it down. D theta dt is your shear strain, or you can say is a strain rate, or you can also term it as uh, rate of angular deformation, rate of angular deformation, right? So you can term it like this. And what is going to be your du dy? Velocity gradient. Okay, see now I'm going to just do some simple calculations. From here I can find that tau is proportional to, okay, let me remove the proportional sign. So you need, if you write equal in place of proportionality, you need to bring in some constants. So a constant will come into play, which is mu du dy. Okay, so from here you can also write it very simply. So I can write that tau will be equal to, here it's going to also be mu and d theta dt. So now if you want to derive from mu, from here, mu equal to tau over du dy. Okay, so from here you can also define your dynamic viscosity or viscosity. So this is what? This is viscosity. This can also further be termed as dynamic viscosity. Okay, so or absolute viscosity can also be its name. Okay, fine. So we have already figured out this equation, okay, and this equation and this equation. Okay, so what is going to be the unit for du dy, or you have already seen du dy or d theta dt. So what is going to be the unit for them? So if you see from here, so du dt, the unit is going to per second. Okay, so if you take a look at them, so the unit is per second. So S inverse 1. So this is going to be your unit, and if you want to write it in terms of dimension, you can also do that. This is going to be T inverse 1. See, now if you want to define this mu, this dynamic viscosity in terms of language, in definition, you will say that, see, take a very close look at this. This mu will become equal to the shear stress when d theta d theta becomes 1. And what is this? D theta dt2, what is this? This is the shear strain rate, or angle of deformation rate. So you will simply say that it is the shear stress, which is required to produce a unit shear strain rate or angle of deformation. You can also define it like this: mu is equal to tau over du dy. So you will say that dynamic viscosity or absolute viscosity is equal to the shear stress when my velocity gradient is 0, sorry, 1. When the velocity gradient is simply 1. If this is 1, then you can say that mu is equal to if velocity gradient is 1, you can say mu is equal to tau at this condition. So you can define this in this way as well. Now let's take a look at the units of dynamic viscosity and kinematic viscosity respectively. So dynamic viscosity can be written like this. We have seen it already. So what is the unit of tau? What is tau? Tau is the shear stress, and stress can be written as force per unit area. So force is having Newton, and area is having meter square as its units. So we can just replace Newton per meter square in place of tau in order to figure out the unit, right? And what is the unit of du dy, which is the velocity gradient, or d theta dt, which is also known as the rate of angular deformation, that is per second. I have already discussed that. So this is per second, 1 by second, this is per second, right? So now if you just rearrange it accordingly, you will end up getting the unit, the desired unit which we are looking for. And this is the unit, Newton second per meter square of dynamic viscosity. Now if you want to write the dimension for this equation, you can very easily write that, right? As I have just given you an example that this is the dimension of Newton or force. Okay, force can also be written like this. So this is actually the dimension of force. So like this, you can very easily replace the terms according to their dimensions and find the dynamic viscosity. Now let's figure out what is kinematic viscosity. Basically, kinematic viscosity, if you want to write it mathematically, you can write dynamic viscosity over the density, which is rho. So this is the mathematical expression. But if you want to know what is the definition will be, you know, the measure of a fluid's resistance to flow under gravity. Okay, so this is what we know as kinematic viscosity. And if you want to figure out the unit for this, so what is the unit of dynamic viscosity? Newton second per meter square. We have written it here. And what is the unit of rho? Rho is kg per meter cube, as it is density. Now in place of Newton, you can write kg into meter per second square, so that you can cancel out kg and kg from here. So how you convert Newton into kg meter per second square? Very easy, right? Because we know F is equal to ma, which is the second law of Newton, although here you will have a summation of forces, but I'm writing it like this. So m is the mass, and mass is having unit kg, and a is the acceleration, which will definitely have meter per second square, right? So you just replace it here. Okay, so in place of Newton, you write kg into meter per second square, and all the rest parameters are same here. So you just calculate it, and you end up getting meter square per second, which is the unit for your kinematic viscosity. Now, if you want to figure out the dimension for this, what is the dimension in case of the kinematic viscosity? That is going to be L square T. Now, let's take a look at the equation for viscosity in case of a linear velocity profile. Okay, so in this case, imagine this illustration. Okay, in this illustration, we can see that we have got a fixed plate, and fluid is flowing through it. So now at this point, this is the velocity profile. We have already discussed about things like this. So as this is your velocity profile, from here I can see that this is my point, and I'm assuming that this point is having some amount of motion, which is du, and the distance from the fixed plate to this particle is the particle of the fluid is dy. Dy is the distance from the fixed plate to this particle point. Okay, and from this point to this point, in which point the I'm assuming the velocity is the highest. So I can see that this is v, and it is having h distance from the fixed plate. So now if you see the Newton's law of viscosity, in this case it will be equal to h by v by h. Okay, v by h is equal to du by dy. How did I get this? Take a look at this. This is a, this is b, this is c. Okay, this is a triangle ABC, and then I'm writing, this point is a, this point is b prime, and this point is c prime. So in the both of the triangles, you see a b C and A, B prime, C prime. In the two triangles, if you follow the triangular law, you will find that V by H, okay, V by H is equal to du by dy. I think it is very easy to understand. Now, if you write F by A in place of tau, which is the stress, because stress is equal to force upon area.